yellowish, actually 0.19 is much smaller than the rest of them. Do you know what? I mean, between 22, like 70, something like that.
Yeah, sorry, so you're asking why, what's up with the gap here?
Yeah, I mean, when you go to higher mass numbers, they are not actually off phase. I mean, they just oscillate together, but when you go to less, the yellow line just disappears and just qualitatively I want to.
I'm sorry, when?
There is the yellow line at low mass numbers, right?
Like here?
Yeah, it seems that it's just much less.
Yeah.
Why is like that?
I don't know. So I mean, it might have something to do with, yeah, these are like seed nucleus masses. So it might have something to do with like having some leftover seed nuclei. You know, this is kind of a marginal value of YE. So you might have like robust neutron capture here, but still have some seeds left over. Yeah, I'm not really sure, and I guess I don't know what happens, you know, below this axis here. So I don't know if this is just, you know, here, or if it's like all the way down here, and you really don't produce these particular species. Yeah, so I'm sorry, that's a good question, but I don't have an answer for you. Okay, right. So I guess one other piece of information we can fold into our analysis of the neutron star merger electromagnetic emission is information from the spectrum. So again, this is some data that was produced in-house. So probably a lot of people are familiar with this, but this is just showing, you know, the time evolution of the spectrum for the kilonova that accompanied GW170817. Okay, so in part, you know, we're just kind of confirming what we already assumed from the light curves. We see that the spectrum seems to have sort of two different components, an early blue component that fades away, and then a longer-lived redder component. But we can get additional information from the spectrum about the velocities of the material that produced each component. So if you look at the blue spectrum, you see that it's pretty featureless. So any absorption features that might be present in the spectrum have been washed out by very high velocities. And based on comparison to radiation transport models, we think that this requires a velocity somewhere around 30% of the speed of light. And if instead you look at the near-infrared spectrum, you see that we still have very broad lines, you know, compared to like supernova, for instance. But they're not so broad that they've completely disappeared. So this still requires a fairly high velocity of order 0.1 c, but you know, a velocity that is still substantially lower than what we see for the blue component. Okay, so combining all of this information, we kind of move towards a coherent picture. We think that we have a high velocity, high YE outflow providing the blue emission, alongside a lower velocity, low YE component that is going to shine red.
Can you say anything about whether it's spherical or not? Are you assuming spherical expansion? Or
right, yeah, so all of the radiation transport models that we're comparing things to are spherical. So we have a little.
There was a jet.
Yes, we know that there was a jet, although that is responsible for like X-ray, radio, and gamma ray emissions. So that's a little bit distinct from the slower outflows that, you know, provide the luminosity from the radioactive transient. We have some guidance from general relativity simulations. Actually, yes, we have some guidance from general relativity simulations about what kinds of geometries that we can expect from these different kilonova components, but definitely an important next step in these modeling efforts is to start to build, you know, more geometrically complicated and realistic kilonova models and look at how that does or does not change the picture relative to what we see in our more simplified spherically symmetric outflow models. Okay, right. So yeah, so we think, you know, the multiple components that we're talking about might be organized something like this. We posit that the blue component could be due to, you know, squeezed dynamical ejecta. So this is material that is squeezed out of the contact interface between the two stars when they collide. Yeah, so you just, you know, they crash together and some material is kind of squeezed preferentially into the polar direction. This material is shock heated, so it's very hot. There's a lot of thermal electron-positron pair production, and that allows weak interactions to raise the YE and prevents this outflow from burning the heaviest high opacity species. I will say this gets a question mark because the amount of mass that was inferred for this component is very high relative to expectations from numerical relativity simulations. So, there have been a lot of other hypotheses advanced about, what could explain this emission, and that's still a very active area of research. But I think something that we can be a little more certain about is the origin of the red component. So in this model, it's due to the outflow from an accretion disk that was formed in the aftermath of the merger. So this, this fits with the low YE required because we know from some new simulations that accretion disks can self-regulate and maintain a very low YE, and therefore successfully have a robust R process that burns through the third peak. And then this is also consistent with the low velocities that we infer from the spectrum of the red component, just because the escape velocities from these accretion disks tend to be about 0.1 C. So let's just take a moment now to rest on our laurels and celebrate, all of the great science that we've been able to do simply from this, one event. So just to summarize a few of the advances, and I'm of course leaving things off because this was, such an amazing event for the whole astronomical community, and there were many, there was a lot of progress that was made. But a few things I want to highlight. We confirmed mergers, in my opinion, as an astrophysical site of the R process. We think this infrared emission is a pretty robust sign of R process nucleosynthesis, and we definitely saw that in the emission from the associated kilonova. We demonstrated an association between mergers and short gamma ray bursts. I think that was in contention for a little while, but later time radio follow-up seems to demonstrate that, a gamma ray burst that was consistent with the cosmological population was produced in this merger. And then we were also able to, take steps towards some of the truly multi-messenger, questions, right? Like driving new constraints on the neutron star accretion state. Okay, so that's very cool, but there are still obviously a lot of questions that remain for us to tackle in the coming years and maybe even decades. So some of these, which we've already kind of, gotten to with questions from the audience, some of these are just, how confident we can be either in analyzing the data and inferring parameters of the kilonova from our observations, and then also how confidently we can extrapolate what we infer about GW 170817 to the full merger populations. But some of these reveal, I think, more fundamental tensions. So in particular, something I unfortunately don't have time to go into in great detail, is the fact that we see signs of R process enrichment in the early universe, as well as in ultra-low mass dwarf galaxies, and this kind of presents a problem for the neutron-star merger scenario, both because it generally takes neutron stars a very long time to merge, and so it's kind of hard to get them to do so promptly. And then also these binary systems receive kicks from their the supernova explosions of their component stars, and those kicks generally should be enough to move them outside some of these low mass dwarfs. So all of this raises the question of whether of whether neutron star mergers are the only R process sources in the universe. And I think this question is particularly salient in light of these first 2 points, and that's because accretion flows around stellar mass black holes giving rise to ultrarelativistic outflows are not found exclusively in merging neutron stars. So I know I'm running low on time, so I'm going to do my best to race through part 3, which will talk about whether collapsars could potentially be an R process source. Okay, so gamma ray bursts, which you could argue are the most direct evidence of these kinds of accretion disks, come in 2 flavors, short and long. We know now that short gamma ray bursts are definitively associated with neutron star mergers, as they've long been theorized to be. And long gamma ray bursts have been associated with a subset of core collapse supernovae, and this association has been known for more than 20 years now. So, observers would refer to these as GRB supernovae or Broadland 1Cs. Theorists often use the term collapsars, which really references a model of how these supernova might launch gamma ray bursts, but it just refers to the idea that you have a rapidly rotating massive star that collapses in its supernova explosion, and the high level of angular momentum present in the stellar material enables the formation of an accretion disk. Okay, so based on kind of, this analogy, a natural question that arises is whether the accretion disks that power long gamma ray bursts could also support an NOR process. Right, so unfortunately, simulating an entire core collapse supernova through the creation and the dissipation of its accretion disk is not computationally feasible right now. But together with some collaborators at Columbia, I worked on a project that tried to do the next best thing, we hope, which was to simulate snapshots in time from the accretion history of a collapsing, rapidly rotating massive stars. And we did this using a full general relativistic magnetohydrodynamics simulation. Okay, so the two questions the simulation needs to answer if we want to really understand, or if we want to argue that collapsars could be our process sources, are first of all, how are we going to achieve the required low electron fraction, right? Unlike in a neutron star merger, in this case we're starting out with high YE material because we're just collapsing a massive star. So we need some way to take that high YE and drive it to low YE. And the second question is, how are we going to maintain that low electron fraction in the face of weak interactions? So this plot of the first snapshot gets at this first question. So, I'm sorry, I'm thinking about how much I have to talk about in this time.
You started about 5 minutes late, so.
Okay, well, I know, but okay. People have some place to be, you shouldn't feel pressured to stay. But, okay, right, so this plot, which is of the first snapshot here, gets at the first of these questions.